Dear friends, this would be an introduction to the ducts in heating, ventilation, and air conditioning systems. You all know that in a HVAC system, the air is processed in the air handling unit. It is commonly called as AHU. And this processed air is then supplied to the space. Let us say it could be a room, or it could be a hall, or it could be a set of rooms which are to be air conditioned. So this requires an air distribution system. And this air distribution system has got four components, namely the supply air duct, the supply air outlet, the return air outlet, and the return air duct. Now, if you look at this diagram, it will be clear, and we have taken a sample room. Let us say this is a room to be conditioned. So what is the supply duct? So let us say that this room has to be maintained at certain temperature Ti and certain relative humidity RHI. This room would be heated or cooled depending upon the ambient condition, and we want to maintain it at a certain inside design conditions. Now, if this has to be maintained at an air conditioned atmosphere, then we need to supply a conditioned air from the cooling coil, or it could be an air washer. So anything which is required for processing this air would be housed in this AC apparatus. So though it is written here that the cooling coil is used here, but it could also be an air washer. And depending upon what kind of psychrometric process is desirable for achieving comfort, this AC apparatus would has to be properly tuned. So this, from this air handling unit, if this is called as air handling unit, to the room, this line would be called as a supply duct. Okay, so this would carry the conditioned air to this room, and hence we will be calling it as a supply duct. Similarly, we would have the unconditioned air. So this air would be, now this air has to be removed from the room, and this has to be returned back to the apparatus for air conditioning. Okay, so this return air which is taken comes from the return air duct. Okay, so this is return air duct is the duct which carries the room air to the air handling unit for recirculation after processing. Okay, so this you need to understand. And then there would be some supply air outlets, and there has to be some return air outlets, obviously, right? Now we would be concentrating here on the ducts part. Okay, so the duct, if you want to understand, we need to be familiarized with the terminology which is used. Ducts could be main ducts, it could be branches, and then there could be a term which is used generally called as index run. So what is it? So the main duct, as the name indicates, would be carrying the major conditioned air when it is a supply duct, or unconditioned air if it is a return duct. And then from this main duct, we will be finding that there are branches. Okay, so this thing which you see over here is the main duct. Okay, and this main duct you see is connected to the branches. So these are the branches you see. Okay, and these branches would be depending upon the load. So suppose this is a space to be conditioned, so this would be a branch. This is some space to be conditioned, so this would be a branch. This is a space to be conditioned, that way. So depending upon the layout of the building, if there are a number of rooms to be air conditioned, we might have this sort of branching. Okay, and the longest branch, longest branch is called as the index run. So this index run term is useful when we talk about the design of the ducts. Okay, so we need to be familiarized with these two terms, namely the main duct and the branches. Now, how do we classify the ducts? Okay, so the classification of the duct is based on velocity. If, for example, these ducts carry low velocity air, right? and by low velocity we mean about 2500 foots per minute, or 760 meters per minute, or if you want in meters per second, it would be around 10 to 12 meters per second. Okay, so the air which is being passed, it has got a certain velocity. Okay, without the velocity the air would not flow. So this velocity would define the classification. So if you have the conditioned air or the unconditioned one flowing with a velocity lower than about 760 meters per minute, then it is called as a low velocity duct. Okay, if the velocities are to be used in practical design, then these are the thumb rules which I have given. For the main ducts, the velocities to be taken would be in the range of 5 meters per second to 8 meters per second. Okay, when we say the low velocity duct, it is below 10 to 12 meters per second. So in the main ducts, for the low velocity ducts, this velocities which are generally taken are in the range of 5 meters per second to 8 meters per second. And for the branches, okay, for the main ducts it has to be higher obviously, and for the branches it has to be slightly lower. So this velocities in the branches is to be taken as 4 meters per second to 6 meters per second. So when you have a low velocity duct, then these are the thumb rules to be followed. Okay, we will study how to select the velocities based on the noise considerations and on other considerations when we discuss the design part. Okay, but for the present study or introduction, we would classify the duct system in the low velocity duct system if the velocities in the main ducts happen to be in the range of 5 to 8 meters per second, and in the branches if it is in the range of 4 to 6 meters per second. Generally speaking, as I said, it has to be below 10 meters per second. Okay, and in foot per minutes, it has to be 2500 fpm. Okay, below 2500 fpm. However, there are applications like ships, for example, where one can afford to use a high velocity duct system. Okay, so in such a scenario, when there is a possibility of using a high velocity ducting system, then if the velocities happen to be above 2500 fpm or above 760 meters per minute, then those duct systems are classified in the category of high velocity ducting systems. So this is the classification of the ducting system based on the velocity. But there is other way of classifying the ducting system. Okay, and before that, let me just point out what happens if the velocities are higher. Okay, how much velocities we need to take. So velocities in the ducts, if you choose higher velocities in the ducts, that would be giving you some advantages and there would be some disadvantages. Now, what are the advantages of going for higher velocities? Now, when you are saying higher velocities, as I said, we go beyond 10 meters per second. Okay, or within the low velocity ducts also, if you are talking about 5 meters per second, that is a low velocity duct, relatively speaking, to 8 meters per second choice. So whether one should choose 8 meters per second or whether one should choose 5 meters per second. So if you choose a high velocity in the ducts, that would result in the smaller ducts. Okay, why is that so? That is because there is in fluid mechanics, you have studied that the flow rate has to be a function of cross-sectional area and the velocity. So Q is equal to, if Q is the flow rate and A is the cross-sectional area of the duct and V is the velocity, then Q is equal to A into V. So if Q is equal to A into V, obviously if the velocities are higher for the given Q, that is for the given flow rates, the ducts would be smaller. So if the ducts are smaller, we would be requiring less of the material, and hence the initial cost would be lower. Moreover, the space requirement would also be lower, because you know that in air conditioning system, the availability of the space is very critical, especially when you are talking about high value kind of buildings like hotels and hospitals, that the space requirement would be critical. So in that scenarios, if we can go for higher velocities in the ducts, that would require less space. Okay, so lower space requirement, smaller ducts, lower initial cost. These are the advantages when you go for higher velocities in the ducts. However, there are disadvantages. What are the disadvantages? One is the pressure drop. So if you go for a smaller ducts, the ducts are smaller, the resistance would be more. And the resistance is more means the pressure drop would be more. And if the pressure drop is more, we need to overcome that pressure drop if the air has to flow. So basically, why do we incorporate a fan into the ducting system? We incorporate the fan into the ducting system so that there is a flow of air into the system. And the flow of air would happen only if the pressure drop is overcome. Okay, so if you are using a smaller ducts, then there would be more pressure drop, and if there is a more pressure drop, we would be requiring larger consumption of electricity for running the fan. And if there is a larger consumption of electricity in running the fan, that is going to increase your electricity bill. Okay, so this is the disadvantage. So if you go for higher velocities, that would result in smaller ducts, but that would lead to higher pressure drops. If that leads to higher pressure drop, that leads to higher consumption of electricity in the fans. That is a disadvantage. The second disadvantage is, as I said, it has to do with the noise. If you go for higher velocities, imagine that the air is flowing with higher velocities, it would make more noise. Yes, one can imagine this. If you experience, for example, the winds, what are winds? So winds are air flowing with higher velocities, and we know that that creates noise. Okay, so when you imagine that high velocity air is flowing in the ducts, that would be giving you more noise as compared to a case where the air is flowing with the relatively lower velocities. So if there is more noise, and especially if you have an applications where we won't be tolerating the noise. For example, if you are designing a ducting system for a library or a study room, okay, then maybe people won't be comfortable with noise. In that case, the high velocities would not be desirable. Okay, so increased noise, and if you have increased noise, then we need to make sure that this noise is attenuated, meaning that the noise is reduced, damped. Okay, and we need to make some arrangements which is called as acoustics, so that there is no noise disturbance in the space to be conditioned. Okay, so that puts in additional cost. So higher the velocities, more would be the noise. So this is how the velocities would impact the selection of the ducting system. And as I said, that is the reason why we classify the duct system based on the velocity, and low velocity duct and high velocity duct. And generally speaking, in most of the applications, common applications, we would have low velocity ducts which are used. There is other way of classifying the ducts, and that is based on the static pressure, and that is based on the pressure which is being overcome by the fan. Okay, so if the pressure to be overcome is this is the gauge pressure we are talking about, not the absolute pressure. If the pressure to be overcome is about up to the static pressure is up to 95 mm of water, or if you would like it in inches, then it is 3.75 inches of water column gauge. Okay, gauge pressure, not the absolute pressure. Then up to 95 mm of water column, if the static pressure is there in the system, then that ducting system is called as a low pressure system, and we would be using class 1 fan for that. Okay, if the pressure difference, if the pressure in the ducting system, the static pressure in the ducting system is between 3.75 inches to 6.75 inches of water column gauge, in mm if you want, the pressure is between 95 mm of water column to 170 mm of water column, then that is called as a medium pressure or class 2 kind of ducting system. Medium pressure or class 2 type of ducting system. And then if you talk about the pressures which are above 3.75 inches up to 12.25 inches of water column, or in mm if you want, 170 mm of water column up to 310 mm of water column, then it is called as a high pressure ducting system. Okay, so this way we have another way of classifying the system as a low pressure ducting system, medium pressure ducting system, and the high pressure ducting system. Okay, the ducts as I said, when we talk about why we should be worried about the classification, we should be worried about the classification because it impacts the air distribution system. Okay, the duct has to be sized. Ultimately, we need to design the duct so that it is accommodated within the available space. Okay, so like any other fluid which is passing through a pipe, for example, if you talk about water passing through the pipe, similarly, the air is passing through a duct, and as I said, this duct would suffer a pressure drop because of friction. Okay, as I talked about, if you want to supply larger quantity of air, okay, through a given cross sectional area, that is a larger air velocity, then the pressure drop would be more, the friction loss would be more, and the pressure drop would be more. Okay, and the fan selected has to deliver the required quantity of air overcoming the resistance. Okay, then the resistance is also offered by the cooling coil, the air washer, if it is air washer type of system. The resistance is offered by the filters, the dampers, etc. Okay, so along with that, if additionally the ducts also offer the resistance, then the fan has to work against that head. And as I said, if the head, that is the pressure to be overcome, which is called as head, as the head increases, the fan would require higher power consumption. The horsepower of the fan would be more to deliver the required quantity of air against the system head or system pressure. Okay, so this we are again stressing because that is why the importance of classification of ducting system is. Similarly, when you talk about velocity, if the velocity increases, we said that the noise level would increase because the air motion would increase. Thus, on the two counts, that is the velocity on the air in the duct has to be kept at a reasonably low level. Okay, with lower air velocities, the size of the duct increases, and so we need to talk about the materials. So the ducting system should be a balance between the material, that is the fabrication, material, erection cost, which is the initial cost, and the operating cost, which is the fan power consumption. So we need to talk about the materials and what are the materials which are used. So if you look at the slide, you find that there are three materials which are primarily used. One is the commonly used duct material, that is a galvanized iron sheet metal. So galvanized iron sheet metal, you will find that it is the most commonly used duct material in the AC industry. Then you would find that aluminum sheet metal is also used. What is the advantage of using aluminum sheet metal over the galvanized iron sheet metal? The advantage is that it would give you the benefit of lighter weight, because you know that aluminum would be lighter, and aluminum would also provide more resistance to moisture as compared to GI. Aluminum would be providing more resistance to moisture. Then you would find that if the corrosion is an issue, and it is a crucial issue in some of the very sensitive kind of environments like ICUs, in that case we might be forced to use stainless steel sheet. Okay, so this is a costly thing. So if you move from GI to aluminum, it would be more costly. The initial cost would be more. If you move from aluminum to stainless steel, the initial cost would again increase. Okay, so choice has to be based on the economics as well as application. So there are some trade-offs. So if you want to sacrifice some comfort, we can gain on the initial cost. But if you want comfort, or if the applications demand that there has to be no compromise on the duct materials, then we need to go for a higher costly materials like aluminum or stainless steel. Some applications like kitchen exhaust, for example, would use heavy gauge black steel. Okay, so in kitchen exhaust you would find that black steel is used, and it is of a heavy gauge. Okay, gauge means thickness. Okay, the thickness has to be more. Similarly, in some places you would find that cement asbestos are used. Okay, cement asbestos are used for underground, especially underground air distribution, and for exhausting the corrosive materials. In some applications, we have found that fiberglass ducts are also used, especially in low velocity applications, and where thermal insulation or acoustic treatment is required. Then one might use fiberglass ducts. Okay. So when you are using GI, the reinforcement cost is also low. Okay, and the joining cost is also low. If you go for aluminum sheets or more heavier stainless steel type of sheets, then we might require uh, uh, more proper joints. Okay, more proper joints, and this joining method. So the simple joining methods cannot be used with stainless steel sheets, right? So ducts used in air conditionings generally are of the rectangular low pressure category, and they generally use only simple joining methods. However, if you are using medium and high pressure ducts, yes, and then steel sheets are exclusively used. As I said, stainless steel sheet, they are used for strength and rigidity to withstand the higher static pressures, because in that case the strength and rigidity would be a issue, since the pressures are higher. And what higher pressures we talked about? We talked about the pressures in the range of 3.75 and above. In medium range, it is 3.75 to 6.75 inches of water column, water gauge, and in the higher pressure, it is 6.75 to 12.25 inches of water gauge. Okay. And similarly, when you are talking about the cross section of the duct, a round duct with its high strength weight ratio is suitable for distribution system. So if possible, if it is always possible, one should use the round ducts, because round ducts are most efficient, as the resistance to the flow of the air is less than the rectangular duct of the same cross section area, because the geometry is such that if it is round, so there is less resistance to the flow of air as compared to the rectangular one. Okay. Uh, However, if you want to use rectangular duct, then it is better to use a rectangular duct of an aspect ratio 1. What does it mean? It means that it is almost square. The cross section is almost square. How does the aspect ratio or the shape of the duct matter? Uh, as I said, the rectangular shape is the most common shape for low velocity ducts. It is easy to construct. The advantage of using a rectangular duct is that it is easy to construct. Rectangular ducts are easy to construct at site, and architecturally it is desirable. Okay. However, the lower aspect ratio allows less material due to lesser perimeter, lesser material due to a higher gauge of shade, lesser material due to less stiffness required to prevent sagging of the shade. Uh, if there is a lower aspect ratio, then there is a lesser cost of installation, lesser insulation cost, and lesser running cost due to lesser pressure drop. So ideally, we should have round ducts. If not, then we should have rectangular ducts with lower aspect ratios, because aspect ratio, if it is lower, then the material cost would be lower. The size of the gauge of the sheet metal would be required would be lower. The installation cost be lower, the insulation cost would be lower, and the pressure drop would also be relatively lower as compared to a higher aspect ratio case. And if the pressure drop is less, then the running cost, the electricity cost would also be less. So this is very important. When you talk about ducts, this aspect ratio is an important term we need to keep in mind. What are the thickness which we encounter? So as a matter of practical advice, I just put in some numbers so that you get a feel of the numbers. Let me just tell you that these are the typical values. Okay, so depending upon the marketplace, depending upon the application, and depending upon the experience of the installer, we might need a lesser or larger kind of thickness. Okay, but what is recommended is, if it is a GI sheet, for example, if it is a galvanized iron rectangular shape, then these are the typical thicknesses. So these thicknesses are generally rated for the long side. So if you talk about the duct size, which is the longer side, of up to 300 mm long side, then we would require a less thick sort of duct. And what is the thickness? It is less thick, means it is a 26 gauge thickness. What do you mean by 26 gauge thickness? 26 gauge thickness of the duct means the thickness is around 0.5 mm. Okay. If you go for a lower number of gauge, means 26 gauge is 26 is a higher number, thickness is lower. If you go for 18 gauge, you see 18 gauge is the lower number, but the thickness is higher. So this is the way industry talks about the gauges. So 26 gauge means 0.5 mm thick, 24 gauge means 0.6 mm thick, 22 gauge means 0.7 mm thick, 20 gauge means 0.9 mm thick, and 18 gauge means 1.2 mm thick. And we are talking about GI. So if you have the longer side of a length up to 300 mm, we would go for 26 gauge thickness. But if you have a longer side, much longer side, above 2100 mm long side, then we need to increase the thickness even up to 1.2 mm thick, that is 18 gauge. So these are the typical values which can be used as the reference values for selecting the thickness of the material. And this is for rectangular duct. And if the material is galvanized iron, if it is aluminum, you would require more thickness. See over here, look at this. Up to 300 mm, the thickness has to be 0.6 mm. Okay, if you compare it to the GI, for GI it is 0.5 mm up to 300 mm long side. Whereas for aluminum, you would require more thickness, that is 0.6 mm thick. If you go on increasing again the longer side length, then the corresponding thickness would increase. So from 24 gauge, it would go to 22 gauge. Then the thickness would increase to 20 gauge if the length is up to 1350 mm. If the length is up to 2100 mm, then the thickness is 18 gauge. And if it is above 2100 mm, then we would require the aluminum rectangular duct of thickness 1.6 mm. Okay, 1.6 mm. Similarly, if you look for the data of round ducts, you would find that such values are available. So such values, recommended sheet metal thickness values for low pressure systems as well as for high pressure systems are available in the literature. So we will not worry about it. There's no need of mugging this up. This values you would get from the reference books, okay, data books. So this was about introduction to the ducting system. In our course, we would be studying some practical tips as well as some theoretical insights, so that we would be in a position to do the duct design on our own. Okay. Thanks for being online. Bye for now.